Okay, hi. So we're continuing on our lecture. Okay, so for 8.1, we are going to study about the rotational kinematics. Okay, so to start off, let's first study about angular displacement theta. So what is the definition of angular displacement? Okay, it is defined as an angle. Okay, as defined as an angle to which a point or a line has been rotated in a specific direction about a specific axis. So let's say you have a rigid body here, okay, and then you have your specific axis there, and let's say we have a particle P, okay, which is moving in an anti-clockwise direction. Okay, so if you want to find the theta here, it should be the arc length divided by the distance from the particle to the rotational axis. Okay, so the mathematical definition here is shown in the next part. So the angle displacement theta is equals to S, which is the arc length, divided by R, which is the distance from the rotation axis. It is noted that it can be at any point because, as we learn in rigid body, it's where all the points of the body rotates by the axis. Okay, so the units of angular displacement is in radians, but it can also be in revolution or in degrees, because we know that the object will complete one rotation or one circle, so it should be in one revolution, which means it completes one rotation, or in degree 360 degree. Okay, so another important things to note here is the sign convention of the angular displacement. If it's rotating in an anti-clockwise direction, so the angular displacement theta is positive. If it rotates in a clockwise direction, that means that the angular displacement theta is negative. Okay, and since we're dealing with three types of unit, which is radian, revolution, and degree, okay, so you need to know lah. Okay, the degree is in 360 degree, radian is in 2 pi rad, and another one, revolution, is in 1 revolution. So you need to know also how do you convert between this unit. So for example, if you have 3 revolution, okay, what's 3 revolution in radian? So 3 revolution should be in 6 pi. Okay, 6 pi. And then you need to know how you convert radian to degrees. Okay, so those things you would explore in more details inside your tutorial classes. Okay, so to continue on, after angular displacement, can you guess what is after angular displacement? Okay, so it is angular velocity. Okay, because we're studying the kinematics of the rotational motion. Okay, so inside angular velocity, there's two terms that you need to know. Okay, but I'm sure that you've already learned here inside our chapter 2. Okay, but that is in linear terms, this is in rotational terms. So the first term is the average angular velocity, while the next term is in the instantaneous angular velocity. So what's the difference between average angular velocity and instantaneous angular velocity? Okay, so let's look first at the average angular velocity. The definition of average angular velocity is the rate of change of angular displacement. So let's say you have initial angular displacement and final angular displacement. If you were to study it, okay, by the rate means that the final minus the initial, okay, per unit time, then you would have the average angular velocity. So what I just said is shown here by the equation, okay, which is the angular displacement final minus angular displacement initial divided by the time final minus time initial. So when we say that we want to find the average angular velocity, it means that we want to find the rate of change. What does the rate of change means? The rate of change means that we want to see the thing at its initial and its final point. Okay, so that is the rate of change. Okay, so it's from the final point minus the initial point of angular displacement and time, where here is the terms definition lah. Final angular displacement, initial angular displacement, and delta t is time interval, where time interval you have time final minus time initial. And what's instantaneous angular velocity. So instantaneous is where we pick the angular velocity at specific point of time, okay, specific point of time or specific position. Okay, we do this. How do you find this? By when the delta t is approaching 0. How do we do this mathematically? It's when we differentiate the angular displacement, or when the limit is approaching 0. Okay, so you find the instantaneous angular velocity by differentiating or by doing limit as it approaches to 0. Okay, so what's the unit of angular velocity? Okay, so we learned in our previous slide that angular displacement, the unit is in radian. But now, since we're dealing with per unit time, so the unit here is in radian per second. Okay, and again, there's also in revolution, right? So there's also revolution per minute or revolution per second. Okay, and it is a vector quantity because now we're not only dealing it with its magnitude but also in its direction. Okay, because we've learned in the previous slide, okay, you have anti-clockwise and clockwise direction, so there's direction involved, so you have magnitude and direction, so it's a vector quantity lah. So how do you determine the direction of the angular velocity? Okay, you use the right hand grip rule. Okay, right hand grip rule. How do you do this? Okay, so in our previous set again, we've learned that when the object is moving inside a clockwise, okay, inside a, let's say we're doing this example, okay, sorry, so it's moving in an anti-clockwise direction, right? So you curl your fingers in the direction of the rotation, okay, and then your thumb would be moving upwards, and that is the direction of the angular velocity. But let's say we were doing it in the clockwise direction. So let's say we're doing it in the clockwise direction. So if you curl your finger in the clockwise direction, you should note that your thumb is in the downwards direction. So the angular velocity is downwards if it's in the clockwise direction. Okay, so that's all for angular velocity. I think you should be able to guess what's our next term. Since we've learned angular displacement, angular velocity, the final term should be angular acceleration. Okay, so again, angular acceleration, there's two terms that you need to know inside angular acceleration, which is average angular acceleration and instantaneous angular acceleration. Okay, so what's the definition of average angular acceleration? Again, we're taking angular velocity, okay, and we want to study it when it's at the final and it's in initial part. Okay, we want to study it, okay, we want to study its change, basically the rate of change of it. So if you want to find the rate of change, again, what I said before is you need to study it at its final and its initial state. Okay, so the average angular velocity or angular acceleration, okay, so there's something, okay, so this is actually alpha, okay, so alpha, okay, sorry, so this is alpha AV. Okay, so the average angular acceleration is omega final minus omega initial divided by t final minus t initial. Okay, where omega final is the final angular velocity, omega initial is the initial angular velocity, and delta t is the time interval. Okay, so what's instantaneous? Again, it's the same thing. It's at a specific part of time or specific position. How do you find this? By differentiating the angular velocity or when the limit is approaching 0. Okay, so now continuing on the units of angular acceleration. Okay, so again, since angular velocity is a vector, so angular acceleration must be a vector quantity as well. So the units is in radian per second square. Okay, and it is noted that when alpha is positive is when the rotation is speeding up. Okay, so it's, if I'm spinning it and it's increasing in its rotation, so the alpha should be positive. But if I'm rotating and it's decreasing with time, that means that the alpha is negative. So it can be shown here that you have your rotation moving here. Okay, if it is speeding up, it means that the alpha is in the same direction as the omega, or the angular velocity. But if it's slowing down, it means that the angular velocity has a different direction towards the angular acceleration. Okay, so we've done our my explanation on angular displacement, angular velocity, and angular acceleration. So now let's see, okay, how do we relate these terms from the linear and rotation? I'm sure that we've learned in chapter 2. Okay, you have displacement, velocity, and acceleration in here because things are moving in a rotational motion. You have angular displacement, angular velocity, and angular acceleration. So we want to see the relationship between linear and rotation. So when a rigid body rotates about a fixed axis, okay, so this is basically our rotational motion in our introduction, okay. All the particle moves in a circular path, okay, which follows the axis, okay, the fixed axis, okay. So here is an example, okay, you have a particle here, okay, you have a particle here, okay, now it's moving in a rotational motion, okay. So at point P, let's say we want to study the ball at point P, okay, located from distance r from the axis O, okay, it moves at a circular arc S and a distance from the axis O R and an angle theta. Okay, so how do you find the angle S here? Okay, you find the angle S here by multiplying the location R with the angle theta. So S equals to R theta, which I'm sure you've learned in your SPM. That is if you remember lah. Okay, so right, you have S equals to R theta, where S is the arc length and R is the distance from point P to the axis O, and theta is the angular displacement. So there's a linear relationship between linear motion and angular and rotational motion. Okay, another thing you need to know that since it's moving in a rotation, but also at the same time the particle is moving in a circular motion, so there must be a linear velocity v, or the tangential velocity. Okay, so from S equals to R theta, let's say if I want to study the velocity, means that I need to differentiate this equation. Okay, I need to differentiate this equation S equals to R theta. Okay, if I differentiate it, because I want to study the angular velocity now. Okay, so if I differentiate it with respect to time, okay, what do I have? I have ds over dt. You've learned inside chapter 2, where if you have the rate of change of displacement, it would be v, right? So this part, okay, is v, okay. Whereas for d theta over dt, okay, the rate of change of angular displacement is omega, which is the angular velocity. So you have here v equals to r omega. So the formula that comes from, okay, the formula here comes from when you differentiate this formula, okay, you can have v equals to r omega. Okay, so where v is the linear velocity of a point on a rotation body, r is the distance from a point of rotation axis, and omega is the angular velocity of rotating rigid body. Okay, so an important thing to note there is that when rotating about a fixed axis, every point on rigid body has the same value of theta, omega, and alpha, which is true because remember our rigid body, right? Our rigid body, okay, you have your axis there, and you have your point particle here with distance r here, right? We have a distance r here, and it moves here as I remember in the previous slide. Okay, and you have here angle theta lah. Okay, sorry for the diagram. Okay, let's just revert back to the previous slide lah. Okay, this slide. Okay, so as you can see, it has the same value of theta, so it's angular displacement. So again, if you were to differentiate it with respect to time, you would have the same value of course, since it has the same value of theta, then it has the same value of angular velocity and angular acceleration, since we are studying it at one point and the axis is not changing. However, it's noted here that but every point has different linear velocity because the r is changing depending on the position of the body. So even though the axis is not changing, however, okay, our object is moving rotational here, right? So the point r is changing here, okay, here the position of the r is changing. It's not the length, but the position of the r is changing. So it depends on the position of the particle. What has it different? Because r is changing depending on the position of particle. Okay, so I'll get back in more detail here. Okay, I'll get back in more details there. Okay, sorry. Okay, ignore what I said in the previous 30 seconds. I'm sorry. So what this means is, let's say if we have another point here, okay, another point here, another point here, another point here, okay, those would have different value of r, okay, so they would have different linear velocity v, okay, so they will have different linear velocity v lah, okay, on that part. Okay, so point P on the rigid body experience two types of acceleration. Okay, so can you guess the type of acceleration that we are trying the body experience? Okay, so this is the body lah, the complex view of the rigid body. Okay, can you guess two types of acceleration here? So you have first the the AT here, which is the tangential acceleration, and then you have here AC. What's AC? If you remember in chapter 6, circular motion, AC is the centripetal acceleration. So those are the two types of acceleration. So tangential acceleration and it doesn't show here. So the first part is the tangential acceleration, the second part is the centripetal acceleration. Okay, so from v equals to r omega, okay, I'm sure, can you try to differentiate this? I'm sure you can do it. Okay, you done? Okay, so if you try to differentiate dv over dt equals to r d omega over dt, if you try to differentiate dv over dt, you would have a. Okay, I'm sure you know that. And again, the rate of change of angular velocity is alpha. So you have a equals to r alpha. Oh my god. Okay, sorry about that. I didn't know that. Okay, so a, they are already back here, equals to, okay, r alpha. Okay, if you differentiate this lah, you have at equals to r alpha, which is at is the tangential acceleration. Then again, since it's moving in a rotation, which is also a circular motion, you will have centripetal acceleration, which is directed towards the center. Okay, you've learned this inside chapter 6. Okay, centripetal acceleration is v square over r, which is r omega square. Since we know that v equals to r omega, right? So substituting that inside here, you would have, okay, r omega square over r. So you should have what? R omega square. Okay, cutting the r square lah. Okay, sorry for the math. Okay, so then how do you find the magnitude of total acceleration? Since we have two acceleration, right? Two acceleration. Okay, one is pointing upwards here. Okay, so this is an example of a plane. Okay, one is pointing here and another point is pointing here. Okay, how do you find the magnitude? The magnitude is basically, okay, a square root square of the component of the acceleration, which we learned in chapter 1. Okay, hope you can remember that lah. Okay, if you want to find the vector here, okay, it's basically a combination of this vector and this vector square root. Okay, and if you want to find the angle again, okay, if you want to find the angle theta here, okay, you just use tangent theta, which is the opposite over adjacent. So the opposite is AT, while the adjacent is AC. Alright? Okay, so the final part inside this subtopic, okay, sorry that it took too much time. Okay, so let us consider a rotating wheel. Okay, so we have here, okay, our rotating wheel. Okay, it's rotating with an initial angular acceleration and a final angular acceleration, okay, and its direction is the direction alpha, means that it is speeding up its rotation, right? So let omega naught be the initial angular velocity at time 0, omega be the final velocity, angular velocity at time t, alpha be the angular acceleration, and theta be the angular displacement, and t is the time taken. Okay, so these are the 4 types of equation of rotational motion. Okay, so you have 1, 2, 3, and 4. Okay, I'm sure you can see almost a similarity in our chapter 2. Okay, but sir, let's say if you have a question, but sir, I don't see the similarity. Okay, let's say, okay, let's say, okay, never mind lah. Okay, so these are the similarity which I'm sure which we have discussed inside this video. Okay, but if you don't know, so these are the similarity. Okay, initial angular velocity is the same as u, final omega same as v, alpha a, and angular displacement s. So if you try to translate this formula, okay, try to, let's say we take this formula and we try to change it to a linear motion. So omega equals to omega naught. So if you try to change it, it's actually v equals to u plus at. Okay, I've seen this before, sir, this formula. Where have I seen this before? Of course, you've seen this in chapter 2. You don't lie lah. Okay, you see this in chapter 2. V equals to u plus at, which is similar to omega equals to omega naught plus alpha t. Okay, so I hope that you understand this video. I'm sorry that it took a long time and there's a bit of things that I've wrongly written. Okay, but that is all you need to know inside the kinematic of rotational motion. Okay, so I'll see you inside your next video, which is okay, so this is explained. So next video, which is torque. Okay, bye.